So hello everyone, and welcome to this first webinar of EO Africa R&D Facility webinar series. And today, during this session, you will have a chance to learn about different capabilities and applications of the software tools for Earth observation analysis. My name is Ewelina Dobrowolska, and I am a junior remote sensing specialist at Serco Italia, and I will guide you through today's session. As my colleague said before, during the webinar, you have a chance to type your questions in the Q&A tab in this meeting. So then afterwards, I will answer them during the live Q&A session. So now I will turn my camera off, and I will move to the presentation. First of all, I would like to present you the outline of this webinar. We will start from the brief introduction to EO Africa project and EO Africa R&D facility. Then I will move to give you an overview on existing open source software tools to be used for Earth observation analysis. Next, I will record the list of webinars which will be provided in this EO Africa R&D Facility webinar series in the future, and provide you with the link to website for registration and YouTube channel where you can find recorded version of past sessions. At the end, we will have about 10 minutes dedicated time for live Q&A session. To remind you, this session is recorded and will last about 1 hour. During the webinar, you have a chance to write your questions regarding to the topic here in a chat, and I will answer them at the end during the live Q&A session. Now, I will briefly describe and introduce you EO Africa R&D facility. So, first of all, what is EO Africa? And EO Africa stands for African Framework for Research, Innovation, Communities and Applications, building an African-European R&D partnership. It is an activity by ESA which aims at fostering an African-European R&D partnership. One of the activities under EO Africa is EO Africa R&D Facility. It is a flagship program of the EO Africa initiative with an overreaching long-term goal for supporting an African-European collaboration. The activity complements other programs, such as GMES and Africa, to enable an active research community and creative innovation processes for a continuous development of Earth observation capabilities in Africa. This project is being developed by 6 partners. University of Twente, as the leader of the project, we have also CS Group France and CS Romania, Serco, TUVN, and Vito. Altogether, 6 partners are going to implement EO Africa facility within 3 years based on the ESA previous experience of the Tiger initiative that provided capacity building through research in Africa in the last 15 years. And now we have EO Africa R&D facility which continue this work. There are 3 main activities that EO Africa R&D facility is going to implement within these 3 first years of the project. The first one is providing a cloud-based Earth observation data analysis environment to support researchers in accessing and utilizing Earth observation data. So the cloud computing platform has been developed, which is called Innovation Lab, and we provide this platform to African and European researchers to be able to perform joint research using Earth observation data in Africa. We also offer technical and financial support for 30 research studies to address African Earth observation research challenges related to water scarcity and food security. The last activity is establishing a digital capacity development platform to provide domain-specific training. And it is established via Space Academy, where we provide face-to-face and online courses, webinars, training modules, as well as MOOCs, massive open online courses. This webinar, indeed, is the third from the webinar series of these capacity development activities. Now, as you know more about main objectives of EO Africa R&D facility, I can move to the actual topic of the webinar, which is software tools for Earth observation analysis. This lecture will provide information about software used for geospatial analysis and Earth observation data manipulation, dividing them into 4 categories. First, you will learn about ESA-supported toolboxes, mainly SNAP, but also other, such as Pulsar Pro, BRAT, or Atmospheric Toolbox, will be introduced. Then we will move to QGIS and plugins dedicated for Earth observation data users. As a third category of software, we will demonstrate Sen2Agri tool used for agriculture monitoring and applied also in African regions. Last but not least, an overview of other Earth observation software will be presented, such as Open Geospatial Foundation, the major provider of open source software for GIS applications, Google Earth Engine, and some selected packages to implement in R and Python that enable satellite imagery processing. Finally, the resources of tutorials and documentation of given software, especially SNAP, will be provided as well on the Moodle platform. First tool I will present you today is ESA SNAP Toolbox, the Sentinel's application platform. SNAP is an ESA open source software for the scientific exploitation of Earth observation missions. In this lecture, you will learn not only about the main capabilities of the software, but also about the software interface, installation process, layout, and available main functions. I will demonstrate you how to open Sentinel-2 product and demonstrate some basic processing and analysis functions. SNAP is a flagship operational desktop software for ESA missions developed by Brockman Consult, CS France, CS Romania, Sensar, and Skywatch. The software was launched in 2003, and it is ideal for Earth observation data processing and analysis due to the following technological innovations: extensibility, portability, modular rich client platform, generic Earth observation data abstraction, tiled memory management, and a graph processing framework. What is important is that SNAP user tool is free of charge and is provided by ESA ESRI to the Earth observation community. SNAP provides a common architecture and basic tools to support not only specific products from Sentinel missions, but also third-party missions. Optional toolboxes and plugins enable processing of such products. So apart from Sentinel-1, 2, and 3 toolboxes, we have also SMOS toolbox and ProbaV toolbox, which can be implemented into SNAP software. The main tool, as well as all other toolboxes incorporated to SNAP, can be downloaded from Science Toolbox Exploitation Platform website. The current version of SNAP is 8.0. The STEP website provides links to SNAP installers. When you click on the main download of the Sentinel toolboxes, you will download the main SNAP platform, which include the Sentinel-1, Sentinel-2, Sentinel-3 toolboxes installers of the size close to 900 megabytes. SMOS toolbox can be downloaded separately. You can see that the software is provided for different operating systems and their versions. With the growing number of Earth observation data users, the SNAP software toolbox has been downloaded more than 500,000 times in less than 5 years. The graphic here represents the cumulative download number by month until the end of March 2020. Certainly, this number has significantly increased until now. From this graphic, you can see that more than half of downloads are made for 64-bit Windows version, where Linux is the second most popular operating system, where downloads occur. Colors in the graph indicate different operating systems. Blue corresponds with Macintosh operating system, green with Linux, red with Windows 64, and yellow Windows 32. Now, we will briefly describe 3 toolboxes built in SNAP software, which are indispensable while working with Sentinel missions. As we have mentioned before, different toolboxes are designed within SNAP to support a variety of products coming from specific satellite missions. Sentinel-2 toolbox is designed to support data handling coming from synthetic aperture radar missions, such as Sentinel-1, NVSat, ERS 1 and 2, RadarSat 2, ALOS 1 and 2, Cosmos SkyMet, Telvasar 10, Tandem 10. Among various tools for processing radar data, it allows to perform fast calibration, code legislation, orthorectification, speckle filtering, mosaicing, data conversion, and polarimetric and interferometric processing. Examples of applications are ice and maritime monitoring, land monitoring, agriculture monitoring, emergency management, floods, fires, volcano eruptions, but also ship detection or oil spill detection. The Sentinel-2 toolbox consists of a rich set of visualization, analysis, and processing tools for the exploitation of optical high-resolution products, including Sentinel-2 MSI sensor. As a multi-mission remote sensing toolbox, it also provides support for third-party data from Rapid Eye, Spot, MODIS, Landsat, and others. Among different functions, it contains also atmospheric correction processor, Sen2 core, L2B biophysical processor, reflectance to radiance processor, and allows also to calculate vegetation, soil, and water radiometric indices, as well as perform pan-sharpening and segmentation operations. The Sentinel-3 toolbox consists of a rich set of visualization, analysis, and processing tools for the exploitation of OLCI and SLSTR data from the Sentinel-3 mission. As a multi-mission remote sensing toolbox, it also supports the ESA mission NVSat, ERS, SMOS, as well as third-party data from MODIS, Landsat, and ALOS. The key functionalities of Sentinel-3 toolbox are visualization spectrum of pixels, doing band maps using arbitrary mathematical expressions, as well as pixel extraction tool, and many others that you can find on the STEP website. Sentinel-3 toolbox can be applied to maritime monitoring, land monitoring, atmospheric monitoring, and climate change monitoring. Now that we have learned about the background of the software, I will actually open the graphical user interface of SNAP tool to demonstrate its layout as well as basic functionalities. When you open the software, you will notice that it consists of 3 main windows. Product Explorer window on the left up corner. This is where you see the list of images when you first open them. You will see also here, in the panel below, World View, where you can see the footprint of the image on the world map. There are also other tabs, such as, for example, Navigation panel, Color manipulation, and Uncertainty information. Then you see the main image viewer. It is where the whole image is displayed. You will also see a number of options in the menu bar at the top. And so if you select, for example, Fire, Import, Optical Sensors, you will see a list of optical missions that SNAP is compatible with. If we select the raster drop-down box, for example here, you can see a list of tools and different functions that are generic to both radar and optical imagery. Whereas in the optical drop-down box, we see the functions specific to optical images, and in the radar, the functions specific to radar images. We will import now the optical Sentinel-2 product to just demonstrate you the basic capabilities of the software. We will do that by going to Downloads, as I had downloaded previously the image of Cape Town in South Africa. So I just drag and drop it in a zip file, you will see that SNAP is able to read also zipped files without need to extract them. And in the second, in the Product Explorer window, the image will be loaded. You can also import the image via Open Product here, or File and Open Product, or import selected optical sensors. For example, you can choose here Sentinel-2 product, and in our case, it will be Sentinel-2 MSI L2A product. Here now you can see the whole name of the image, and here we can see a little plus icon where we can expand the folders of the product. We see the folder containing metadata, and if we just double click on this, you see all information about this product. So you can see, for example, the start time of sensing, then you can see the processing level, product type, and so on, and other product characteristics. We can close that window. And here, for example, in the folder bands, you will see all 13 bands which are stored in the Sentinel-2 product. If we double-click now on selected band, for example here, the image is open. But from this image, the visualization is not that straightforward. So to visualize, for example, product in natural color bands, you just need to navigate to the name of the product in Product Explorer window again, right-click on it, and select Open RGB Image window. Here now you can see you can select Sentinel-2 MSI natural colors, and it takes as a red band, band 4, as a green band, band 3, and blue band 2. So it creates a band combination. You click OK, and now you can actually see the visualization in natural colors. Here you can see the Waterscroft Dam. You can also go to the window, and for better visualization, you can tile horizontally both images on the left and on the right. And to synchronize those two visualizations, you just need to go to View, Synchronize Image Views, and Synchronize Image Cursors. And now when you move over the area of your image, then you see that it will zoom both images on the left and on the right. And you can see how they are represented in different band composites. You can also perform very quickly some basic operation on this Sentinel-2 product. And for example, I can demonstrate you resampling. So if you go to raster, then you go to geometric operations and resampling. Here we can resample the whole 13 bands into the same pixel size. So if we go to, now here we don't change anything. Here in resampling parameters, we for example choose band 2. Here we don't save the product, so we will just demonstrate it quickly, and we click Run. And we see that the operation has been performed. Now we close those products, and when we open it, the new resampled product, and we would like to visualize the image, now we have the whole selection of different band composites, as they all have the same resolution. So for example, we can select now land-water visualization, land-water band composite. And here you see that we have band 8, band 11, and band 4, which we will use. We click OK. And we also can select other band composite, for example, false color infrared. And we click again OK. We tile horizontally both windows. And now we can see that we can distinguish better water areas from agriculture, for example, or vegetated areas. So you can see very clear the border of the dam. You have also options here to export the product, for example, to different formats. It allows you to save an image in GeoTIFF, in JPEG, and other formats. Now, for example, when you zoom in into the Waterscroft Dam, and for example, you would like to have only this subset of the image instead of storing the whole Sentinel-2 acquisition, then you just zoom in into the area you're interested in. You just can right-click on this, and here you can select Spatial Subset from View. Here you can see that this subset will be selected. Now when you go to Band Subset tab, and you select none of the band, and then you just select the bands band 2, 3, 4, and for example 11 and 12 and 8, and you click OK, this subset will be created, and here you have a new product that has prefix subset. Now we will close this, or this I will leave open, and I will just open this product here. We go again to Open RGB Image window, and we select Natural Colors. We click OK. And now you can see that this image actually has been cutted to this size only to cover the area of the Waterscroft Dam. OK, so I will minimize this window now and come back to the presentation. Moreover, processing tools which I demonstrated to you before in graphical user interface could be run also independently from the command line or Python script. SNAP can also be run in Graph Processing Tool, GPT, that allows to execute a number of SNAP operations in batch mode without opening Java Graphical Console. Dedicated Python package Snappy has been developed to automatize processes in ESA SNAP tool and bring it to Python script. Also recently, a community-developed project appeared which provides an easy and Pythonic way to write and run SNAP graphs using Python. This GPT wrapper for Python is called Snapista. Another tool which has been launched by ESA to support processing of SAR data is PolSAR Pro. This stands for Polarimetric SAR Data Processing and Education Toolbox. Contrary to previously presented toolboxes, this toolbox is a standalone application and it is not implemented within the SNAP platform. This software has been developed in 2003 under the contract between ESA and the Institute of Electronics and Telecommunication of the University of Rennes. The software contains a collection of well-known algorithms and tools, establishes a foundation for the exploitation of polarimetric techniques for scientific developments, and stimulates research and applications developments using PolSAR, PolInSAR, PolTomosAR, and PolTimesAR data. It runs on Windows and Linux operating system, and it can be run on graphical user interface or command line. PolSAR Pro supports the future ESA Biomass mission and third-party missions, such as ALOS-1, Cosmos SkyMed, RadarSat-2, Telesat-10, and Tandem-10. Next ESA toolbox I would like to present is BRAT, which is Broadview Radar Altimetry Toolbox. It supports missions from ERS-1 and 2, TOPEX, GeoSat Follow-On, JSON-1 and 2, ENVISAT, CryoSat, and Sentinel-3 mission. The key functionalities of the software is that it is open source, freely available software available in 32-bit and 64-bit versions for Windows, Mac, and Linux. It incorporates the capability to read the Sentinel-3 Level 1 and Level 2 products. It is designed to read radar altimetry data and to perform simple operations for altimetry and for oceanography. It includes the radar altimeter tutorial, which contains an extensive introduction to altimetry showing its applications in different fields. You can apply this software to study the Earth shape and size, gravity anomalies, bathymetry, ocean circulation, operational oceanography, mean sea level rise, and greenhouse effect. It also provides near real-time computations of wave height and wind velocity, as well as dual frequency altimeters are used to acquire rain rates. More application can be found also on the website of this tool. The last ESA toolbox, which I am going to present you today, is Atmospheric Toolbox. And Atmospheric Toolbox aims to provide scientists with tools for ingesting, processing, and analyzing atmospheric remote sensing data. The toolbox consists of several software components: CODA for direct reading access to product data, HARP for ingesting, processing, and intercomparing satellite or model data against correlative data, VISAN for visualization and analysis application for atmospheric data using Python, and DUAS perform DUAS retrievals of trace cases from spectral measurements. Some of the data supported by the toolbox are products from satellite instruments such as TROPOMI on board of Sentinel-5P, EOLUS, GeoMi-2, and OMI. But the toolbox also supports model data such as CAMS and data from ground-based instruments such as provided by EVDC. Now, when you are familiar with different tools supported by ESA, we will move into most commonly used software for remote sensing and GIS applications. This software is called QGIS, which stands for Quantum GIS. It is an open-source GIS desktop platform developed by the Open Source Geospatial Foundation. It runs on different operating systems, from Linux, Unix, Macintosh, Windows, and even Android. Application has user-friendly interface with over 900 community-driven plugins to facilitate particular analysis or enable certain functionalities of the software. It supports and integrates different spatial information formats such as vector, raster, and spatial databases. The application itself provides users to indeed use different sources of data, integrate them, and perform spatial analysis and visualization. However, what is most important, with a variety of plugins developed by the software's community, some more advanced analysis can be performed and used in Earth observation. They allow to download satellite data coming from different sensors directly in QGIS desktop application without need to search for them in dedicated platforms. They allow also to pre-process satellite imagery, even atmospheric correction can be performed. They allow to integrate and visualize products from different data sources, perform geostatical computations and image analysis, as well as perform supervised and unsupervised classification. Now, you may ask me question how to install such plugin in QGIS application. So I will briefly demonstrate this process. I will close for now the presentation and will navigate into QGIS application I have installed. The process doesn't change even if you have different version of QGIS software. Now, to install any plugin, you just need to navigate in the main menu bar. You just need to navigate to Plugins, Manage and Install Plugins, and here new pop-up window will be opened. First of all, go to Settings and check the box Show also experimental plugins. Now go to All, and here you can search for a plugin. You can see that we have available 1030 plugins. So it depends on the version of your QGIS desktop application. Here we can, for example, select the plugin Semi-Automatic Classification plugin, and we see here its description. To install a plugin, just click on Install, and the installation process will start. Now you can see that here below the main menu, we have additional options, and here we have also a layout of the plugin. Here we have user manual, you can ask the question and go for a support for this plugin, and here you have different options to use. Now I will minimize this window and I will come back to our presentation to just demonstrate you a selection of plugins which are widely used in Earth observation applications. So coming back to the presentation, first of all, I will present Open Layer plugins, which is very useful and gives an access to base maps coming from different map services from Google Maps, Bing Maps, Apple Maps, Wikimedia, and OpenStreetMaps. Using this plugin, you can geolocate spatial datasets, and it helps also to navigate and prepare data visualization, as it can be treated as a background layer in your project. And to briefly show you this, I will come back to QGIS, and you can also go to Manage and Install Plugins. Here you can write Open Layers plugin, and here you can see that it is experimental plugin, but we can also access it. So we should click here Install Experimental Plugin. Now you have the information that plugin was installed successfully. We can close this window, and to open that, we just go to Web, Open Layers plugin, and here you can see, for example, Google Satellite. And here you can navigate through the map. Here you can see the Africa, for example. If you had also a vector layer, you will see it here, and then you can zoom in to your area of interest. For example, you can change also to OpenStreetMap, and this will look differently. We will zoom in, for example, to the Cape Town, and here you can see how it looks like, the OpenStreetMap. So it can be used also very good as a background to your visualization which you want to prepare. Another important plugin is Sentinel Hub, which is nothing else than extension of Copernicus Data Sentinel Hub, cloud-based application programming interface for Sentinel imagery. It is developed by Synergize, and it enables to connect with Sentinel Hub server directly from QGIS desktop graphical interface. However, it requires registration on the Sentinel Hub website beforehand. Once you are registered, then you will be able to download Sentinel mission products based on predefined criteria: area of interest, sensing period, cloud cover, and sensor type. You can also define the image format or resolution of the product you would like to get. Another indispensable plugin, especially when it comes to processing of satellite images, is Semi-Automatic Classification plugin. As it might be suggested by the name of the plugin, it not only allows to perform classification, both supervised and unsupervised, but it also makes it possible to download data from different satellite missions, including Sentinel, Landsat, MODIS, Aster, and others. It is a Python-based plugin which incorporates GDAL, which is raster and vector library, SciPy, NumPy, and Matplotlib, which are modules for scientific and mathematical computing and plotting. Some tools also require the installation of SNAP software. What is more, plugins allow us to perform pre-processing of images, cloud mask, resampling, atmospheric correction, and others. Band processing, such as band combination, stacking, but also classification, and allows to generate classification accuracy reports or computation of land cover changes. Below you can see the examples of use of such plugin. Another broadly used plugin is JetSaka classification tool. It uses variety of classification algorithms to perform semi-automated classification, such as Gaussian mixture module, random forest, support vector machine, key nearest neighborhood, and other predefined classifications. The plugin is based on Python programming language and requires the installation of scikit-learn library before starting the classification on your machine. To perform simple classification with this tool, you just need to have a raster image and a shapefile with your area of interest. The Earth Observation Time Series Viewer is the last plugin that I will show you today. It is used for visualization and labeling raster-based Earth observation time series data. This plugin is a very handy tool when you would like to visualize multi-sensor time series of Landsat 7 and 8, Sentinel-2, Rapid-Eye, and Pleiades observations. This tool automatically extracts timestamps from image metadata. It uses GDAL library and supports about 142 raster formats. What is more, it allows for visualization of multiple band combinations in parallel, for example, true color and color infrared. In previous slides, only a few of plugins available in QGIS were described, but there is plenty of other tools which facilitate working with satellite-based imagery. Here you can find again a selection of them. Among many others, you can find, for example, Google Earth Engine plugin, Google Earth Engine Time Series Explorer, Send-to-Core adapter for atmospheric correction, or Pulsar tool. Dedicated plugins to support basic operations on raster data also exist. There are, for example, tools to extract single pixel values, such as Value tool, creating raster stack, such as one-click raster stacking plugin, or calculation of raster statistics, for example, raster stats. What is important is that each plugin has its own GitHub repository, so source code of each plugin is publicly available. All plugins are under continuous development. QGIS community is very active on this field. You can find the newest updates always in the plugins window, but also on GitHub and on the plugin repository, which stores all plugins available in QGIS. In this part of the lecture, we will focus on Send-to-Agri system developed by ESA to support agriculture monitoring with satellite imagery. Agriculture is particularly important remote sensing application, especially because of international attention about food supply. Land grabbing over the world challenges national food security in many countries. That is why better agricultural monitoring capabilities are needed, and here is where Earth observation can help. ESA satellite match Earth observation requirement for agriculture monitoring for most countries, especially Sentinel-2 mission, which provides images in high resolution 10, 20 and 60 meters in a 5-day revisit cycle. Sentinel-2 is also compatible with Landsat missions, which provide additional information on agricultural status in the area we are interested in. That is why Send-to-Agri has been developed to combine functionalities and opportunities of both missions, Sentinel-2 and Landsat 8, and apply them in near real-time agriculture monitoring. Send-to-Agri is an acronym of a software called Sentinel-2 for Agriculture, which is an open-source system launched by ESA as a major contribution to R&D and national capacity building components of the GeoGLAM initiative and GCAM network activities. It is a standalone application operating under GNU General Public License and compatible with Linux-based environment. It is also integrated with the previously described Sentinel-2 toolbox. It has been tested on Amazon Cloud, IPT, EODC, which is a private cloud, and DIAS, so not only local processing is possible. Send-to-Agri processor is used to generate 4 agriculture products from Sentinel-2 A and B missions and Landsat 8, using time series along the growing season. These products produced by the processor are monthly cloud-free surface reflectance composite at 10 and 20 meters, cropland mask binary map at 10 meters updated every month, crop type map at 10 meters for the main regional crops, which also allows to determine irrigated or rain-fed crops, vegetation status map at 10 meters, which are delivered for each acquisition every week. And how the system works. Sen2Agri is operating in two different modes. Automated mode for operational applications running graphical user interface, and manual mode, which allows for more customization of given parameters and allows to run different processors in the system independently. System consists of 4 independently executable component processors, which are managed and executed by orchestrator, and then provide 4 different products described before. Now we will present more details on how the system works on the example of crop type mapping. Tool is working in 2 stages. The first stage is to define the initial parameters, so study area, monitoring period, and data type required by users or Sentinel-2 or combination of Sentinel-2 and Landsat 8 products. During the campaign, so the field monitoring period, also uploading field data for the classification of crop type is necessary. The system works in the following way. Sentinel-2 products are required and atmospherically corrected. Then during the first months, system accumulates data, perform pre-processing, and at the mid-season will provide the first crop type map. Then it continues to download and process data for the second half of the monitoring period and produce a second map at the end of the predefined season. From this product, it is possible to receive also crop area indicator at mid-season and at the end of the season. Later, all those products can be combined and gives a chance to perform crop-specific monitoring. System was tested in about 12 tested sites, relying on GCAM network spread over the world, which represent more than 17 major crop types. Last part of this theory lecture will be selection of other open source software for Earth observation analysis. To start this topic, open source Geospatial Foundation project needs to be introduced. This non-profit, non-governmental, community-driven project formed in 2006 brought a huge range of tools and capabilities which now are applied in most, if not all, GIS and remote sensing software. Over the years, this organization developed separate projects which can be divided into particular groups. Desktop applications, among which we can find flagship QGIS application and GIS software, software to manage spatial databases with tools called PostGIS, the geospatial libraries, Geospatial Data Abstraction Library GDAL, which is a critical GIS infrastructure which supports more than 200 raster and vector geospatial data formats and is used in over 100 different GIS processing tools. PLOCH, another particularly important open source library which allows to perform transformation of geospatial coordinates from one coordinate reference system to another, Orfeo Toolbox, an open source project with a wide variety of remote sensing applications. Last but not least, OSGeo project developed also web mapping applications, among which we can find Map Server, OpenLayers, or GeoServer. One of the very commonly used tools among Earth observation data users is Google Earth Engine, cloud computing platform which combines large catalog of satellite imagery and geospatial datasets with computational power to process and analyze those images. Thanks to various capabilities, Google Earth Engine makes processing of satellite imagery available for scientists, researchers, and developers to detect changes, map trends, and quantify differences on the Earth's surface. The platform uses Python and JavaScript application programming interface and allows to use the power of Google Cloud to perform geospatial analysis. Most of the capabilities of applications presented before can be applied also in Python or other programming languages. Particular tools can be implemented with dedicated modules or libraries. Python has dedicated tools for geospatial analysis, such as GeoPandas for operations on geospatial data, Cartopy to produce maps and other geospatial data analysis, PySal, the Python Spatial Analysis Library for open-source cross-platform geospatial data science, GeoPy provides popular geocoding web services, GDAL, a translator library for raster and vector geospatial data format, and Ploch, cartographic projections and coordinate transformations library. There are also other tools which are used by Earth observation data users, which are scientific computing packages. They are also broadly used by statisticians and also for data manipulation. There are, for example, NumPy, which supports large multidimensional arrays and matrices, Pandas, data analysis library that structures data in data frames, facilitating further computations, Matplotlib, comprehensive library for creating static, animated, and interactive visualizations in Python, Xarray, which facilitates working with labeled multidimensional arrays, and SciPy, scientific computing and technical computing. Then we have also packages that facilitate machine learning applications. Those are, for example, scikit-learn, which includes easy integration with different machine learning programming libraries like NumPy and Pandas, TensorFlow, it is end-to-end open-source platform for machine learning, advanced functionality for deep learning models and neural networks is provided, Keras, which is one of the most popular and open-source neural network libraries for Python. It extends the usability of TensorFlow with additional features for machine learning and deep learning programming. And PyTorch, which is an open-source machine learning library based on Torch library, used for applications such as computer vision and natural language processing. Other packages, which refer to image processing, are following: EOLearn, which provide access and process spatiotemporal image sequences acquired by any satellite, Rasterio, which provides access to geospatial raster data, Scikit-Image, which provides a collection of algorithms for image processing, RasterStats, which allows summarizing geospatial raster datasets based on vector geometries, and OpenCV, which is an open-source library for computer vision, machine learning, and image processing. Similarly to Python, also our developers community came across the needs of Earth observation data users. There are several handy packages which can be used while working with satellite data. Those are the tools for basic data manipulation, such as raster, for creating, reading, manipulating, and writing raster data, SF or simple features, which replaced SP package, spatial aggregation of thematic information in spatial objects. Then we have RGDAL, bindings to the geospatial data abstraction library, AddGeos, interface to geometry engine open source GEOS, MapTools, which provides set of tools for manipulating geographic data, and shapefiles to read and write SD shapefiles. As in case of Python, we have also packages for cartography and data visualization applications, and those are, for example, ggplot2, which creates plots and maps using the grammar of graphics. Then we have rasterviz, which enables visualization methods for raster data, tmap, which is thematic mapping using grammar of graphics syntax. Then leaflet creates interactive spatial visualizations with pop-up windows for attribute data, and cartography creates cartographic representations with typical map elements. What is more, there are also other useful packages, such as tidyr, to simplify the process of creating tidy data, Plotly for creating interactive web-based graphs via the open-source JavaScript graphing library, Deepler, tools for working with data frame-like objects, both in memory and out of memory, Cadet package to perform machine learning algorithms in R, and Send2R to download and pre-process Sentinel-2 optical images. As you might have noticed, it was a very brief overview on just a small selection of existing tools for processing satellite imagery. To close this webinar, I would like to remind you that this webinar you have participated in was the third from the EO Africa R&D Facility webinar series, as I mentioned at the beginning, and here you will find a list of past webinars which are already available to watch on our YouTube channel. The registration for the next webinar on evapotranspiration from space, methodology and products is already open, so you can register for this one if it fits your interests. It will take place on Friday, 25th of March, so in 2 weeks from today. Here you can find a list of planned webinars, so I encourage you to follow the EO Africa R&D website to find out more about future events which will be announced one after another. Now, as I told you, we have dedicated time for live Q&A session, so now I will go to the chat to read all the questions you post related to the topic. And in case you have more questions, please do not hesitate to ask, and I will try to answer them in a minute.
Thank you, Evelina. We do have a few questions. You want to have a glass of water before you start with?
Yes, sure. I will just.
I can read the questions and you answer them.
Okay.
Yeah, I have another 5 or a few more minutes to do this. So the first question I got was, is it possible to develop and add my own plugin in SNAP?
Mm-hmm. Yes, so SNAP has a broad community that support the plugin developments. So if you go to the STEP forum, you will find a way there how you can develop your own plugin. But there is also a broad selection of already existed plugins, so you can also have a look there. So yes, if you are able to write in Java, then you can use the plugins in SNAP, your own plugins. But of course, you can also apply SNAP into Python script, where you can as well manage and develop your own algorithm while using, for example, SNAP-E package. So there are many ways. This is an open source software, so this under continuous development. And I refer you to STEP forum to see more about it.
The other question, so that question was from Jospen, and this is the same person asking, can we process Sentinel-3 images in QGIS? And if so, which plugin can we use? Okay, so for Sentinel-3 images, you can as well process them, I think, within the okay, it's within QGIS. Sorry, I just confused with SNAP. So with QGIS, I think there is a Pulsar Pro plugin, so you can try in there to process the Sentinel-3 images, but. Yeah, I am not sure if, for example, other plugins are supporting QGIS. You can also check in the QGIS forum, because I am not that familiar with processing Sentinel-3 data, so I do not want to confuse you. Okay, the next question from Partik. As far as, as I know, the Poisar Pro output product needs an envi header to work on QGIS. My question is if there is any predicate template available to easily load the data on different GIS software. Thanks.
Okay, so you can always try to use the Pulsar Pro toolbox without using it on QGIS because of any other different GIS software. I do not know if there is any other plugin than this Pulsar Pro, but this is also under continuous development as far as I know. So probably with the new version of it, it will be available. But you can also check on the toolbox of Pulsar Pro toolbox and process there your data.
Next question of Partik. Can you please describe how to process the phase unwrapping with SNAP after processing the InStar product on SNAP?
Okay. For this, I think I'm.
Is this fit for this presentation?
Yeah, I didn't touch this this topic. I am not that familiar with SNAP in the InStar products, so I would refer to check in the STEP forum. They have quite good support on this.
Okay. Next question from Selabalu. Can the presentation be shared, especially because there was a lot of plugins? And, oh, yes, it will be shared online.
Yes,
it's being recorded. What are the so from Cyan, what are the different ways that are available in Sen2Agri or SNAP to monitor agricultural fields?
Yes, the monitoring of agricultural fields, it's quite a broad topic, so it depends which data you would like to use and which methodologies to apply. For example, you can also use a Jupyter notebook, and in Python you can develop your own algorithm. You can perform time series or apply different vegetation indices to monitor agricultural fields in SNAP or in Sen2Agri. As you have seen, you can perform crop mask or you can perform the crop type classification. So yeah, there is this is a huge topic. So it depends on your application, which software you would like to use. So you can also use simply QGIS and semi-automated classification plugin if you would like to classify your crops. For monitoring as well, you can perform time series as well in the, for example, in the Google Earth Engine or in other softwares. So there are plenty of them.
Okay, one question from Cornelis. Is it possible to monitor this expansion of small crop fields, smaller than 50 meters, annually using Sen2Agri?
Yes, if the Sentinel-2 images and Landsat 8 provide you that data that you think there are sufficient to crop that small fields, of course you need to take into account that you need to have as well the training data. So like this, the monitoring will be more accurate if you have ground truth data. With Sentinel-2, it might be difficult to monitor such small fields, but of course it depends. It depends on your area of interest. So you may explore and check if the classification or monitoring is sufficient for your application.
Okay, and now for the last question, which is on the chat, from Gordon. Excellent presentation, he says. I agree. I am interested in selecting the relevant EO tools to monitor the coastal tidal flux over a defined period to integrate with a study to monitor bird activities in fragile coastal wetlands in the context of climate change in the Southern Africa region. Looking forward to identifying and establishing tools.
Mm-hmm. Yes, this is very complex study, as I see. So yeah, in order to perform such an analysis, I think you will need to integrate many different tools. So of course, field data, I think this will be necessary to have, but yeah, again, to monitor the coastal, for example, changes, you can always refer as well to our to the website of RUS training website, and we have there on the YouTube channel, we have as well there different webinars on the topic of coastal changes. You can have a look. It is not running now, the project, but you can still rewatch the videos recorded. For the bird monitoring. I think you would need to perform a field study and then just integrate it maybe with QGIS and other tools. But yeah, this is very specific. So I think you need to search more as well in the literature to identify.
So we are 5 minutes over time already, even though we started 5 minutes late as well.
Yeah.
So that gives us one time a full webinar. Any closing comments, Evelina?
Yes, I hope you have enjoyed that webinar, and I hope you have learned something. Of course, I know that there was a broad range of them, and there are other existing tools that I didn't mention, but the Earth observation has still growing community, and new tools are out there. So for specific applications, you may find also different software. So I hope this you will find useful, and I hope you have enjoyed. I wish you a pleasant afternoon as well. And I hope you will also follow the EO Africa other events and register for the upcoming webinars. So thank you very much.